Welcome back. Next, I want to talk about more examples on method of differences in section point 7.2 of your notes. Before I begin, I would like all of us to look through example 7 on your own and also very quickly look at example 8, first part, which is the expressing in partial fractions, which answer is given here very easily. So pause the video and look through example 7 before carrying on. Okay, I hope you have gone through example 7 on your own. Let us take a look at example 8, and I assume this first part, partial fractions, is not difficult. Assume knowledge, you will get this. Now you need to use the result, which is the result of your partial fractions, to show this. So again, we take a look at this summon here. Looks almost the same as this. This is actually this, right? Almost exactly. Um, it's just short of a 2 here. So what a trick we can do is to say this is equals this one, which is what you want, half of this with a 2. Once you create the 2 out, it will exactly be this expression over here. Now remember what I said in the earlier video when we will use method of differences when you can express the summon, which is here, as anything in the summation, as a difference between 2 or 3 terms. And so far, the example in 6 and 7 are always difference between 2 terms. Now I'm going to illustrate, actually it can be done with 3 terms as well. Don't be scared. Let's see how this can be done. If you write it down, the half remains, of course. Let us write term by term. You sub r equals to 2 here, you get half minus 2 over 3 plus 1 over 4. Next one, 1 over 3 minus 2 over 4 plus 1 over 5 plus 1 over 4 minus 2. The trick again, I would like to emphasize, one value of r, one line. This is r equals to 2, r equals to 3, r equals to 4. You're not going to carry on, you will just plus dot dot dot, and then followed by the last 3 terms. Right? Second last term, and finally the last term. Now here, I want all of us to pay close attention how to cancel. If you write the terms properly, like they're starting from r plus 1, r plus 2, you will realize that this 1 quarter plus 1 quarter, you get 2 quarters, minus 2 quarters, you will realize that it cancels very nicely this way. And then you have 1/5, right? Minus 2/5. There must be a 1 over 5 here. If you don't believe, you see one half, 1/3, 1 quarter, this one must be 1/5. So this one also cancels. Similarly for the 1/6 here. Similarly for here, you will see 1 over n, 1 over n, minus 2 over n. Surely this one will also go. At the end of the day, right? At the end of the day, you will get this 1, 2, 3, 1, 2, 3 terms. 6 terms. You get simplify, you will get this. And then ultimately you will get the final answer. Now, I want to emphasize this cancellation can still be done with 3 terms. Next, let us talk about the next 2 parts. Explain why it's convergent as well as show this. All right, let's talk about this next 2 parts. Now, give a reason why, pardon the bell, give a reason why this series is convergent. We want to know what, whether this series is convergent. Meaning what? Meaning, suppose if you see n, if n is 10, Suppose only, yeah. Then this one must be 10, 10. Is if n becomes very, very big, will this, that means you sum all the way to very, very, very many terms. Will this sum of the series converge to a specific value? That's all you are trying to find. All right. So you ask yourself, as n tends to infinity, or as n tends to infinity, I'm not going to explore whether this one tends to zero or not. It's not about this guy. It's about the sum. It's about this one. Correct? If n is 1000, then actually you sub 1000 in, 1000 in, 1000 in. If this converge to a specific number, then that series is convergent. So I want to say that as n tends to infinity, then 1 over 2 n plus 1 n plus 2 actually tend to 0. Right? Because if you have some very big number here, this whole thing tend to 0, which actually then means that your sum, your series here, actually tend to 1 over 12. Therefore, the series is convergent. The sum to infinity is just 1 over 12. Next, you are supposed to show that this whole thing, no matter what is n, is less than 12. Now, I want to contrast the phrasing between these two. This first part asks you whether the series is convergent or not. Whether it's converged. That means if you sum to 10, sum to 100, sum to 1000, does it converge to a specific big value? Now, the next part asks you to show that no matter what is n, it is always smaller than 12. I repeat, no matter what is n. So the moment you say the next part, if you want to answer it like as n to infinity, wrong already. You can't. We are not interested in as n to infinity for this last part, right? So how do you say? You say for all positive integers n, right? Because they want you to show no matter what is n, this sum will always be less than 12. For all values of n, this is wrong by the way, then you say, look at this expression here, 1 over 2 n plus 1 n plus 2 is always positive. Correct this one. Then you get 1 over 12 minus something always positive will always be smaller than 12. Right? Hence, your expression here will always be smaller than 1 over 12. This is the most important. This one is the most important. I want to emphasize for all positive integers n. Can we please contrast the presentation between these two? Some more example. Let's look at example 9. Pardon, this video may be a little bit longer, but please hang on. Right? You need to show that for k larger than 1, this fk minus 1 is this. Now, fk is some complicated looking thing. Now, I'm not going to focus so much on this exercise. Why? Because it's all algebraic manipulation. Okay, you just make them into a common denominator, blah, 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 blah. I want all of us to just accept that this one is just algebraic manipulation, which is not difficult. Okay, suppose you've shown it. Go through the algebraic manipulation. I don't think it's difficult. I want to focus on part 2 and part 3 now. Right, let's take a look at part 2. Hence, find this. Okay, there's a hence, find this. Now, recall from part 1, you have already shown that fk minus 1 is this. That means this one can go this way. Meaning to say this one, which is exactly the same as that, can be expressed as fk minus fk minus 1. So I'm going to jump straight to this. I don't even care at this point what does fk mean. What is the function f? Actually, don't not that it doesn't matter, but it doesn't matter now. So it's quite obvious if you've done enough MOD, some method of difference, this summon is now expressed as a difference. And you would know quite quickly if you've got experience, excuse me, with from experience, you are there, therefore this is f1 minus f0 plus f2 minus f1 plus f3 minus f2, and then your last two terms, fn minus 2 minus fn minus 3 plus fn minus 1 minus fn minus 2 plus, oops, plus fn minus fn minus 1. And you can see here that it cancels very, very nicely this way. And what you are left with is a minus f0 plus fn. Therefore, it is a fn minus f0. Now, at this point, then we dig out what is fn. Fn from the definition earlier is basically what you get here. You will get a 4n plus 1, n minus 1 over 3n plus 2. F0 is 4, 1 minus 1 over 3, 0 plus 2. Now, blah, 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 you simplify. I don't want to go through the simplification. You will get your answer. So from here to here is simple manipulation, algebraic manipulation. I don't want to go through, but I want to highlight this idea of cancellation. Even though you don't know what is f at this point, you just write f1 minus f0. And then you will get this answer. Right, that is example 9, part 2. Example 9, part 2. Let us now take a look at part 3. Use your answer in part 2 to find this. Now, maybe I retrieve, maybe you can take a look now. From part 2, this is what we get. Now you want to find this one. Notice the phrasing, use your answer. From here, you cannot do another MOD. Why cannot? Because the question asks us to use your answer. That means you are literally going to use this answer from part 2. This is from part 2. The result from part 2. So the moment you start from here and you say, oh, I want to do another MOD, I know how to do another MOD. Wrong, cannot. Not that it's wrong. The question doesn't allow you to do that. So I want to put here pay close attention, because this is traditionally the part that many students don't know how to do and get very, 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 very confused. Okay, so let me try and help you. Okay, the way to do it is this. Let us first write the terms out. Okay, step 1. Write the terms out. Meaning what? Meaning it's very, very long, I can understand, but it's okay. Let's try. That means this is what you want, right? You just substitute k equals to 1 inside here, which is a 2 square, 4 to the power 2. Don't need to evaluate. I just write the terms out with just the numbers without evaluation. like that, right? Plus, don't write too many, just write two terms enough already. Then just focus on the last term. No need to think so much. Focus on the last term. N plus 1 square for n plus 1 over n plus 2, n plus 3. I think step 1 is quite easily understood. Write the terms out. No need too many, right? Just first two terms and then write last term. Now, next step is then important. Step 2. All right. You write it in the form of part 2. Meaning what? Meaning the question already tell us to use your answer in part 2. So somehow you got to change this into this form. Only then can you make use of this result. I say one more time. Somehow you're going to change what you have written here, which is the same as this, in this form. The moment you express it in this form, you will get your answer, which is here. So I am going to write like that. Notice I do this. Notice that when I do step 2, notice I deliberately leave out the upper and lower limit because I don't know. At this point, I don't know. I repeat one more time. At this point, I don't know. I deliberately leave out. Next, oh sorry. Next, I am going to find out. I am going to write out what are these two limits. Okay. Next, I'm going to do that. So how do I do that? It's not that difficult. We already wrote out the terms here, and we already suspect. In fact, I'm pretty sure this whole thing can be expressed in terms of this. That means this one, not this summon. It's this summon, right? Then we test. What k do you substitute here such that you will get this first term? The answer very simple. You sub k equals to 2. Right? Because you sub k equals to 2, you get 3, denominator get 3 times 4. Numerator you get 2 square, 4 square. Correct. No problem. Check. K equals to 3. You get 4 times 5, which is the denominator here. Sub 3, 3 square, 4 cube. Now then you ask yourself, what do you substitute into into k such that you get last term here? The answer is n plus 1. You sub k equals n plus 1, your numerator becomes this, your numerator becomes this. You sub k equals n plus 1 into a denominator, you get n plus 2, n plus 3. So we're done. So you were right. Here, I will say blue first, then red. Okay? I will say blue first, then red. That means you write the summon first, then decide the limits according to what you have written above. Then that's it. Once you have gotten this, I think the answer is out. Why? Because if you know this is n, if this is like that, this is equals to this, I can change the n to y, then all the n change to y. But now the n is a n plus 1. But we're not totally done yet because this is k equals to 2 and this is k equals to 1. Right? Yes? So first I will have to subtract it out like that. K square 4k over k plus 1 k plus 2 minus away the first term, which is the 1 square for 1 over 2 times 3, which works out to be 2/3. But here, from here onwards, we are done, because as long as this is n, I can change the n to m, I can change the n to x, y, I can change the n to n plus 1. So this is 4 n plus 1 plus 1, n plus 1 minus 1 over 3, n plus 1 plus 2 plus 2/3 minus 2/3. Final answer is what? 4 n plus 2 n over 3 n plus 3. Replay this video if you need to understand this completely. The key thing is in step number 2. Okay, from here to here. Thank you.